In this video, we want to study about the physical properties of the molecular compound. Two main physical properties that we want to discuss here are the melting point and the boiling point and solubility of the molecular compound. The melting point and boiling point of any substance depends of the attraction between its base unit. For the molecular compound, the attractions which are available between the molecules are intermolecular forces, which are relatively weak force of attraction. So that's why most of the molecular compound they have low melting point and boiling point, and most of them are gas at room temperature. This is in contrast with the ionic compound. In the ionic compound, we have the ionic bond, which is strong electrostatic attractions in the lattice structure. So it's not easy to separate the cation and anion from each other, and the ionic compound they have higher melting point and boiling point compared to the molecular compound. So let's move on to the next page and do this work example to become more clear about the melting point and boiling point. In this work example, the question is put the following molecules in order of increasing boiling point and explain your choice. So three molecules are given here. The first thing that you must know here is that these functional groups CHO and OH. CHO is aldehyde functional group and the structure of that one is given here. And OH is alcohol functional group or hydroxyl and the structure is shown here. Okay, so let's compare the boiling point and melting point of these three molecular compounds. So we know that all of them are molecular compounds. To compare their boiling point, we have to look at the intermolecular forces which are available between their molecules. Let's start from the last one, CH3, CH2, CH3. This is the hydrocarbon, and you know that the hydrocarbons are non-polar molecules. So the only attractions which are available between the molecules of the CH3, CH2, CH3 is London dispersion forces. The next one, CH3CHO, which is aldehyde, the force which are available between its molecules is London dispersion forces plus dipole-dipole attraction. So this shows that the attraction between these molecules is more than the attraction which are available between the propane CH3, CH2, CH3. And the alcohol, as you can see here, the hydrogen is connected to the oxygen. So when the hydrogen is connected to electronegative atom of oxygen, there are hydrogen bonding between the molecules. So this compound not only have London dispersion force, but it also has dipole-dipole attraction because the molecule is polar, and it has hydrogen bonding because the hydrogen is connected to the oxygen. So based on these intermolecular forces which are available here, we can find that the CH3, CH2OH or alcohol has highest boiling point between these three because it intermolecular forces are stronger than the other. Then aldehyde, and the last one is this hydrocarbon. So you can see the order of the boiling points here. On the other hand, some of the covalent bonds are available between the giant molecular compound, giant structure like the diamond, like the silicon dioxide. The base unit of these compounds are atoms, and there are strong covalent bond between the atoms, and when you want to melt them you have to overcome these covalent bonds, which is not easy to do that. So that's why most of the giant covalent compound they have very high melting point. For example, the diamond remains solid until about 400 degrees. So Above 400 degrees, the bond between the carbon atom in diamond starts to break up. So when you want to compare the melting point and boiling point of two materials, first you have to check what is the type of the material. Is it giant covalent structure? Is it ionic? Is it molecular compound? Is it metal? And if all of them are in the same category, then you can compare them. Otherwise, you know that the giant covalent compound, for example, has much more higher melting point and boiling point than the molecular compound. Let's move on to the next properties that we want to discuss here, and that is the solubility of the different materials. There are one general rule available for the solubility, and that is like dissolves like. It means the molecules which has same type of the attraction between the molecules can dissolve in each other. For example, the nonpolar substances are soluble in the nonpolar solvents, and polar compounds are soluble in polar solvents. And the molecules which can have hydrogen bond is soluble in the solvent that can form the hydrogen bonding. So it means like dissolves like. But why nonpolar substances are able to dissolve in nonpolar substances? Because both of them have London dispersion force, and the London dispersion force forms between the solute and solvent, so they can be easily dissolved in each other. Same thing can happen for the covalent compounds. When you mix two covalent compounds, when the solute is covalent, it's polar, and you want to put it in the polar solvents like the water. Water is an example of a polar solvent. There would be dipole-dipole attraction between the molecules of the solute and the molecule of the solvent. So polar solute can be dissolved in the polar solvent like the water. But what happens if you put non-polar solute in the water? So we are putting non-polar molecule in the water, which is a polar solvent. Because the attraction between the water molecules, dipole-dipole attraction and hydrogen bonding is much more stronger than the attraction that would be between these non-polar molecule and the water. The molecule of the solvents remains together, and non-polar solute cannot be dissolved in the polar solvent. On the other side, the molecules which have hydrogen bond can be easily dissolved in another solvent which can form hydrogen bonding like the water. So that's why the alcohols which has the hydrogen bond and it can form the hydrogen bond, they are very soluble in the water because there would be the hydrogen bond between the solute, alcohol in this case, and polar solvent, in this case the water molecule. So we can say if the polarity of the molecule is big, it's more soluble in the water. So some of the molecules, they have polar area and they have non-polar area. The famous example is the alcohols that you can see here. So look at the alcohol. This part of the alcohol is hydrocarbon. So you know that the hydrocarbons are non-polar. But this area of the alcohol is polar, the hydroxyl group, and it also can form hydrogen bond with the water. So if this non-polar area is small, the solubility in the water is big. But if you have an alcohol which the hydrocarbon chain is very big, for example, this heptanol, it has 1, 2, 3, 4, 5, 6, 7 carbon, and then it has OH. I don't put the hydrogen here, it has CH2, 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 CH3. So you can see this one also it has OH, so it can form the hydrogen bond with the water, but its non-polar area is very long and very big. So the solubility of this alcohol is much less than solubility of the ethanol, the structure that you can see here. Okay, so it says the difference in solubility is due to the size of the non-polar hydrocarbon group. This is very important, especially for dissolving the alcohols in the water. And as I said before, the non-polar covalent compound do not dissolve well in the water, which is polar solvent. That's why the solubility of N2 and O2 in the water is very low, and they can be slightly soluble because of the dipole-induced dipole attraction, but this attraction is very weak. So most of the hydrocarbons which are polar, like the wax, they are not soluble in the water. Most of the chemicals that can stain the clothes are non-polar and they cannot be dissolved in the water, like the chlorophyll, for example, the red wine, the grass stain, the grease. All of them are non-polar molecules, so they cannot be soluble in the water. As we say, they are insoluble non-polar molecules in water. At the same time, the polar substances have low solubility in non-polar solvents. So if you have a polar solute and you put it in the non-polar solvent, they have very limited amount of solubility. So we can say they are not soluble because the particle of the solute held together by the dipole-dipole attraction and cannot interact well with the solvent. So that's why you cannot dissolve, for example, the sugar inside the oil. The oil is non-polar solvent, sugar is polar solute, so their solubility is very small, so we say they are insoluble. Another group that we want to talk about that is giant molecular substances. Giant molecular substances are not soluble neither in the polar solvent nor in the non-polar solvent. So they are not soluble, and you can see the sand SiO2 which you can see at the beaches are not soluble in the water. The diamonds also are not soluble in the water. So be careful when we are talking about the solubility and they ask you if something is soluble in this solvent, you cannot simply say it's soluble or not because of like dissolves like. You must talk about the intermolecular forces. If the solute is non-polar, solvent is non-polar, you can say that both of them has London dispersion force of attraction between each other, so they can be soluble in each other. If you have polar solute and polar solvent, you can say that both of them can form dipole-dipole attraction between each molecules of the solute and solvent, so they can dissolve in each other. If you have a molecule which can form hydrogen bond like the alcohol, it can be dissolved in the solvent which can form hydrogen bond like the water, so they can be dissolved in each other. But if the solute is polar, it cannot be dissolved in the non-polar solvent because the solutes are held together by the strong dipole-dipole attraction and you cannot dissolve it in the polar molecule. There is not a big interaction between the solute which is polar and solvent which is non-polar. And same at the same thing, you cannot dissolve the non-polar solute in the polar solvent because the polar solvents are held together by the dipole-dipole attraction, and the attraction between them and solute are very limited. And for the giant molecular substances, because the atoms are held together by a strong covalent bond, it's not easy to break them and have another attraction with the solvent, so they are non-soluble. The next topic and physical properties that we want to talk about that is electrical conductivity. The covalent compound, molecular covalent compound, they do not contain the ions and they don't have the net charge on the molecule. There can be dipole, but the overall molecule is neutral, so they are not able to conduct the electricity in the solid state or even in the liquid state. Same thing we had for the ionic compound in the solid state. Although we have charge in the ionic compound, but because they are fixed in their position, they cannot move and they cannot conduct electricity. But some of the molecular compounds, when you put them in the water, they produce the ions. The famous examples are acids, for example, hydrochloric acid, hydrogen chloride. When you put in the water, these two parts separate from each other. We say they dissociate into H plus and Cl minus. So I write aqueous here. It means in the water, these two parts separate from each other. And also we can say they ionize to H plus and Cl minus. In that case, when you put these molecular compound in the water, the solution becomes conductive. It's exactly the same when you put the ionic compound in the water. It becomes Na plus aqueous plus Cl minus aqueous. The cation and anions separate from each other and they become free to move. So they become conductive when you put them in the water. But if the molecular compound dissolves in the water and it doesn't produce the positive and negative charge, its solution is not conductive. For giant molecular compounds, most of them are not electrical conductive, and you know that we had some exceptions like graphite and graphene. They are conductive because they have free electron and they have delocalized electrons which can move throughout the material. And also fluorine and silicon, they are semiconductor. They are not very good electrical conductor, but they are semiconductor. The rest of the giant molecules like SiO2, diamond, they are non-conductor of electricity. So summary of the physical properties are given here for four types of the materials that we have. The ionic compounds, polar covalent compounds, non-polar covalent compounds, and the giant covalent. So these two which are written at the middle, they are molecules. The metals are not written here, so I want to add the metal to the last part. Okay, and be careful that this table is very general. You may have exception in each case. To understand the physical properties, it's very good to know what are the base unit for each one of them and what are the attraction between their base unit. For the ionic compound, the base units are ions, cation and anion, and the attraction is ionic bond. So you have ionic bond here. For the polar covalent compound and non-polar covalent compounds, for both of them, you have molecules at their base unit, and the attraction between the covalent compounds are dipole-dipole attraction. You may also have the hydrogen bonding, and for the non-polar covalent compound, the attraction between the molecules is London dispersion forces. For the giant covalent compound, the base units are atoms, so it can be different atom or one atom like the diamond, and the attraction between the atoms are covalent bond, which is strong. And for the metals, the base unit is metal ion in C of electron. And the attraction between the metal ion and C of electrons are a strong electrostatic attraction. So, based on these attractions which are available between their base unit, we can predict their volatility. Volatility is ease of vaporization. So when we say something is very volatile, it means it can be easily go to the gas phase. Ionic compounds, they have very low volatility because of the strong ionic bond which are available between the ions. For the giant covalent, they have very low volatility because of the strong covalent bond which are available between the atom. For the metals, they have low volatility because of the strong attraction between the metal and sea of electrons. But for the molecular compound, their volatility is high. Okay, and it's written highest for nonpolar covalent compounds because the attraction between the nonpolar covalent compounds are weaker than the attraction between the polar compound. London dispersion force compared to the dipole-dipole attraction or hydrogen bonding. Okay, solubility in the polar solvents like the water. Ionic compounds are soluble. You know that you can easily dissolve table salt in the water. For polar compound, they can be dissolved in the polar solvent like the water, and solubility increases as the polarity increases. But non-polar covalent compounds, they are not soluble in water. And the giant covalent, they are not soluble. Metals also not soluble. So for example, iron doesn't dissolve in the water, metal iron. Solubility in non-polar solvents, ionic compounds are not soluble in the non-polar solvents. Okay, they are not soluble. So that's why you cannot dissolve the table salt inside the oil. They are not soluble because the ions in the ionic compounds held together by the strong ionic attraction and ionic bond, and it prevents attraction between the ions and non-polar molecules in the solvent. Polar covalent compound, they are not soluble in the non-polar solvents, but if says solubility increases as the polarity decreases, it means if it becomes less polar, it becomes more soluble. Here we are talking about the length of the hydrocarbon chain. So the polar compounds are not soluble in the non-polar solvent like the hexane. But if the length of the hydrocarbon chain increases, for example in the alcohol, it becomes more soluble and more soluble. Non-polar compounds, they are soluble in the non-polar solvents. Giant covalent compound, they are not soluble, and the metals, they are non-soluble in the non-polar solvents. Okay, the electrical conductivity, ionic compound, in the solid state, they are not conductive, but when you melt them in the liquid state or when you dissolve in the water in aqueous, they become conductive. Polar compound and the non-polar compounds, the molecules, they are not electrical conductives, but if you dissolve a molecule in the water and it produces the ion like the HCl, it can be conductive in the solution. Giant covalent compound, as you know, they are not conductor of electricity except graphite, graphene, and silicon and fluorine, which are semiconductor. And the metals, you know that the metals are very good electrical conductors because they have free electron, they have sea of electron, they have delocalized electrons. So they are electrical conductive in the solid state and in the liquid state. Let's go to the next page and answer these exercises and we will finish this video. Question number 27 says the physical properties of the five solids labeled A, B, C, D, and E are summarized below. The substances are an ionic compound, non-polar molecule in the solid, metal, polar molecule solid, and the giant molecular substances. So you have five type of materials here. Okay, based on the properties which are mentioned here, you must be able to diagnose each one of them. The important things that you can use are the conductivity of the solid. Between these five types of the material, only metals are conductive in the solid state, and some of the giant molecules like the graphene and graphite. But this is the main property of the metal. The metals are electrical conductive in the solid state. So between these five type of the material, only A is written to be conductive in the solid state. So its probability metal, its solubility in water is insoluble. So this emphasizes that it can be metal, and its melting point, it says third to melt. So when it says third to melt, it's obviously not giant molecular substance, because the giant molecular substance has the highest melting point. So we identify A, it's metal. Okay, so we find the metal. Let's talk about the ionic compound. One of the very specific properties of the ionic compound, that they are not conductive in the solid state, but when you dissolve them in the water, they become conductive. Okay, so they are soluble in the water. So between the C and E, which is written soluble, one of them is the ionic compound. Look at their conductivity. For C, it says it's not conductive, but for the E, it says it's electrical conductive in the solution. So this shows that this one is an ionic compound. Conductivity of the solid state is not conductive. Okay, this is very important properties for the ionic compound. In the solid state, they are not conductive. In the solution, they become conductive. And its melting point is written fourth to melt. So this can be ionic compound. So we found the ionic compound as well. Okay, so let's move on to the nonpolar molecules. You know that the nonpolar molecules are insoluble in the water, which is polar solvent, and B and C are insoluble in the water. But for the B, says the melting point is the highest. For D, says the melting point is the lowest, and you know that the nonpolar molecule has the lowest melting point. So the D is nonpolar molecule. So I hope that you guess what is B. The B must be the giant molecule, because it's insoluble, it's not conductive in the solid state, and it has highest melting point. So this highest melting point is a very good sign to identify the giant molecular structure. And for the C, obviously it's polar molecule. It's soluble in the water because polar molecule dissolves in the polar solvent. Conductivity of the solution, they are not conductive. In the solid state, they are not conductive. And it says its relative melting point second to melt. Okay, this one is a little bit challenging, because you know that the polar molecules, they have a low melting point. Okay, but maybe these polar molecules are very big, so it has strong London dispersion force, for example, that cause it to be second to melt. Question 28. Which substance is the most soluble in the water? Four substances are given here. Substance B and C are non-polar, so they are not soluble in the water at all. A and B, both of them are alcohol, and you know the alcohols, because they have hydrogen bonding, they are very soluble in the water. Also, they have dipole-dipole attraction with the water molecule. But between these two alcohols, the difference is the length of the hydrocarbon chain. This one has only one carbon, this one has two carbon, and you know when the length of the hydrocarbon chain increases, the non-polar properties of that molecule increases, and it becomes less soluble in the polar solvent like the water. So the most soluble substance in the water is A. Question 29. State the intermolecular forces that exist between the molecules of each of the following. Dry ice CO2. You know that CO2 is nonpolar molecule, so the only force of attraction between its molecule is London dispersion forces. NH3, it's a polar molecule, so it has London dispersion force, dipole-dipole attractions, and also hydrogen is connected to the nitrogen, so it can have hydrogen bonding. N2 is non-polar molecule, it has only London dispersion forces. CH3OCH3, it's ether, although it contains the hydrogen and oxygen, but the hydrogen is not bonded to the oxygen. So this molecule can have London dispersion forces and only dipole-dipole attraction. It doesn't have hydrogen bond. And the last question, question 30, which of which of each pair has the lower boiling point? So for A, we are comparing between two hydrocarbons. The hydrocarbons are non-polar, so the only force of attraction between their molecules is London dispersion forces. And when the molecule becomes smaller, the London dispersion forces becomes weaker and the boiling point also becomes lower. That's why C2H6, which is a smaller molecule, it has weaker London dispersion force and it has lower boiling point. For part B, we have H2O and H2S. Both of them are polar molecule, so both of them has London dispersion forces. But H2O also has hydrogen bond, so that causes the H2O to be to have higher boiling point to compared to H2S, which doesn't have the hydrogen bonding. So that's why H2S has lower boiling point. Part C, Cl2 and Br2, both of them are non-polar, and for the non-polar molecules, the smaller molecule has weaker London dispersion force and has lower boiling point. So that's why Cl2, which is smaller than Br2, has the lower boiling point. And for the last one, HF and HCl, both of them are polar molecules, so they have dipole-dipole attraction. Both of them has London dispersion force. The London dispersion force of HCl is more than HF because Cl is greater and bigger than HF. But more importantly, there are hydrogen bond between the HF molecule which cause its intermolecular forces very strong, stronger compared to the HCl, and it would have higher boiling point. That so the answer for this question, which one has the lower boiling point, is HCl because it has weaker intermolecular attractions.